The current standard for AI-assisted development is a highly iterative loop, often called vibe coding. A developer writes a prompt, and the agent instantly reacts, churning out code as fast as the API allows. This immediate reactive cycle skips the planning phase entirely. When you ask for a feature, the underlying large language model must make architectural assumptions on the fly. These rapid-fire assumptions inevitably introduce structural flaws. The developer then has to intervene, sending a flurry of follow-up prompts to correct the design choices the model just executed. The LLM's context window, its working memory, is a finite resource. Every round of recursive bug fixing pushes more conversational data into that memory. It rapidly fills with prompt corrections and discarded code, leaving less room for actual application logic. Kiro is an opinionated fork of VSCode built specifically to solve this token degradation. Backed by Amazon, it is designed to strictly manage the AI's state. It shifts the AI from an autocomplete generator into an integrated systems engineer using 3 core mechanics: Spec Pipelines, dynamic steering, and event hooks. Scaling AI across a codebase is not a problem of generating syntax faster. It is an economic challenge of optimizing token allocation and maintaining the agent's focus. The first mechanic is the spec. Instead of a direct prompt-to-code execution, Kiro enforces a mandatory structured Markdown pipeline. This flowchart visualizes how Kiro splits a single user prompt into a sequential process. It translates raw business requirements into a formalized technical design, which then generates a precise, actionable task list. Take a classic example, asking an agent to build a hangman game. When given this prompt in spec mode, the agent completely halts syntax generation. Before writing code, it explicitly maps out the software architecture. During the design phase, the agent actively establishes interfaces. It sets up an MVC pattern, defining a dedicated game controller and a language manager to separate core logic from the user interface. A standard reactive chat interface would skip this step and output a single monolithic script that becomes impossible to scale. By resolving structural ambiguity before execution, the spec pipeline drastically reduces downstream token burn. The process requires a longer planning phase up front, but it eliminates the need to run recursive prompt loops to fix poor architectural choices later. The spec pipeline trades initial speed for long-term stability. It ensures that the LLM's context window is filled with deliberate, formalized plans rather than a chaotic log of corrections. As a project scales, developers often try to enforce consistency with massive global system prompts. This approach wastes API costs and actively degrades the LLM's reasoning capacity by overloading it with irrelevant data. Kiro solves this with steering. These are modular, per-project Markdown files that codify domain-specific rules. A developer working on a Python application like Flask requires consistent typings and docstrings across the entire codebase. A standard coding agent forgets these conventions after a few interactions, unless the developer manually repeats them in every single prompt. This diagram illustrates Kiro's dynamic scoping mechanism. Steering files operate as situational filters, injecting specific rules into the working memory only when they are relevant. When the system detects that you are editing a Python file, the logic gate triggers the Python steering module. It injects structured coding standards directly into the data stream. Simultaneously, pattern matching prevents irrelevant rules from bleeding in. SQL formatting rules are actively blocked, preventing the model from getting confused.
Writing these rules from scratch is straightforward for a new repository. Integrating steering into a mature, legacy codebase requires a different approach. Instead of manual data entry, Kiro autonomously scans an entire repository to map the existing product structure and tech stack. This scan condenses thousands of lines of code into a standardized 30-line context primer. It outlines file naming conventions, architecture patterns, and test execution commands without any manual setup. Dynamic steering economically manages the LLM's attention. By injecting only the exact constraints required for the active file, it guarantees high context fidelity. The final architectural layer extends the agent's utility beyond syntax generation and directly into the broader software development lifecycle. Kiro achieves this through hooks, event-driven background tasks tied to specific triggers within the IDE. Consider a standard REST application. A developer updates an endpoint for a search listing and saves the backend route. This diagram shows the system architecture in action. That basic file save event emits a signal that awakens a dormant background agent listener. Operating asynchronously, the agent parses the new route and automatically updates the YAML documentation file. The developer never leaves their active task. Automating peripheral tasks introduces an inherent risk. Allowing a generalized agent to execute complex third-party API logic often causes the model to hallucinate expected parameters. To mitigate this, Kiro uses powers, which are specialized implementations of model context protocol servers. This visual shows a discrete MCP power module slotting into the main agent workflow. It acts as an isolated sandbox that bundles specialized external expertise, like custom domain-specific language syntax or precise Stripe API constraints. When a developer invokes a Stripe power, the agent can create a product price and generate a payment link with absolute precision, without having to guess the exact structure of the external API. Crucially, these powers are loaded dynamically only when requested. This keeps the core IDE context window pristine and unbloated by external libraries. Hooks and powers transform the editor into an active automation platform. They safely delegate engineering overhead to background processes, preserving the agent's main context for active development. Kiro shifts the AI tooling landscape toward vertically integrated engineering, using a system of architectural state management to provide control that transactional chat lacks. This diagram illustrates how the mechanics work in unison. Specs define the architectural plan, steering enforces the domain rules, and hooks execute the peripheral actions. This interconnected architecture shifts the burden of maintaining structural consistency off of the human developer and directly onto the framework of the IDE itself. The primary friction point for developers adopting this tool is that it requires a steeper learning curve and forces them to adapt to a highly opinionated workflow. This demanding structure stands in sharp contrast to the immediate gratification of standard conversational chat interfaces. Unstructured chat is sufficient for writing isolated scripts, but it critically fails when navigating the interwoven complexity of mature, enterprise-level codebases. The ultimate value of this system lies in its token economy. By strictly managing state, it protects the LLM from its own tendency to drift and hallucinate. Imposing strict state management on AI agents ensures that context is treated as a finite resource. It provides a structured path to scaling software development as codebases grow beyond the limits of a single prompt.